Hello everyone, greetings from my side. I'm Dr. Shanshan Zhao. I'm currently a postdoctoral researcher at Seoul National University Power Electronics Center at the Department of Electrical and Computer Engineering. Today, I'm really honored to be here to give the presentation. Today's topic is on the modular multilevel DC-DC solid-state transformer with inherent bipolar operation capability for resilient bipolar MVDC grid. My presentation consists of 4 sections. I'll start with the research background and then introduce the MMC-based DC-DC SST with inherent bipolar operation capability, followed with the experimental verification, and finally a brief summary. The increasing penetration of the renewable energy such as wind and solar, as well as massive demands for diverse DC loads such as electric vehicles, data centers, and energy storage devices impose higher flexibility requirements on power systems. The distribution technology can reduce the power conversion stages in the grid integration of the distributed renewable generations, energy storage systems, and DC loads. Besides, it presents remarkable advantages such as higher efficiency, higher power quality, higher flexibility, and thus has broad application prospects. The MVDC distribution system generally include the monopolar configuration and bipolar configurations. Compared to the monopole configurations, the bipolar DC terminal is able to provide more available voltage levels. Thus, the flexibility of the system can be enhanced. On the other hand, due to the independent operation of 2 poles, when one of the poles is faulty, instead of shutting down the whole system, the remaining pole can still operate and maintain at least 50% of the rated power, which largely enhances the reliability of the system. In the MVDC distribution system, the DC-DC solid transformer is one of the key enabling components. A typical 2-stage DC-DC SST consists of 2 DC-AC conversion units with the AC terminals interconnected by a medium to high frequency transformer. The DC-DC SST not only provides voltage matching and galvanic isolation required by the distribution system, but also features reduced size and weight due to the high frequency AC link, as well as higher controllability thanks to the power electronics converters on both sides. For the application of the bipolar DC grids, DC-DC SST should also have the capability to realize bipolar operation and meanwhile to withstand the medium voltage level. To realize the bipolar operation capability of the DC-DC SSTs, 2 approaches can be applied. The first one is to implement a DC-DC voltage balancer on a regular monopole DC-DC SST. The one shown in the bottom left figure is the typical topology. It can actually be considered as a buck converter with 50% duty cycle and can maintain the DC voltage balance of the 2 poles if asymmetric power consumption arises. Despite the simplicity in power regulation and the plug-and-play feature, requires an extra medium voltage power electronics converter, which will introduce considerable volume and cost. Therefore, the second approach, which is to use a DC-DC SST with inherent bipolar operation capability, tends to be a more attractive solution. And to withstand medium voltage level, 2 candidates are widely considered, which are cascading modular type and a modular multilevel type. The left figure shows a typical input series output parallel topology of the cascading modular type DC-DC SST. Although they features flexible scaling of power and voltage ratings due to the modular structure, each transformer suffers from a different DC bias with respect to the ground. However, in modularized mass production, the installation level should be designed considering the worst case. So this could result in significant waste regarding to the space for air isolation as well as bushings. Comparatively, modular multilevel-based DC-DC SST also features high scalability and easy redundancy thanks to the modular structure. Since the magnetic coupling can be concentrated in a single central transformer, the overall insulation design of the whole system can be optimized, and therefore the MMC topology is discussed as the medium voltage interface. However, as is well known, the conventional MMC-based DC-DC SSD does not include the bipolar operation capability, so an extension of the topology is necessary. There are mainly two types of existing solutions. Number one is to use two sets of MMCs and two transformers on the primary side to form an input series output parallel structure. And the second solution is to use also two MMCs, but with the triple-winded transformer. The first solution requires two individual transformers with insulation capability for a medium voltage DC bias with respect to the ground, and also it requires two individual MMCs on the MV side. And this results in a complexity of the conversion station and installation efforts. And for the second solution, despite that only one transformer is used, both windings on the primary side are also subject to the medium voltage DC bias with respect to the ground, and the complexity of installation efforts still remain. Moreover, since the powers of the three ports of the transformer are tightly coupled as in a triple active bridge, the power control becomes challenging. Therefore, an MMC-based DC-DC SST with inherent bipolar operation capability is presented here as an alternative approach. The application of interconnecting a bipolar MVDC grid with a low voltage distribution grid is just here as an example. And therefore, the MMC is used on the medium voltage side and the full bridge is used on the low voltage side. A conventional operation scheme of this topology is to use the phase shift modulation, where the power transfer from the medium voltage side to the low voltage side is controlled by manipulating the phase shift angle between the AC voltages of both sides. The upper and lower arms operate symmetrically and transfer the same amount of power. However, is it possible for the two poles to transfer different amount of powers and can be regulated independently? Based on the phase shift modulation principle, it can be assumed that if we applied an additional phase shift angle between the AC voltage of the upper and lower arm of the MMC, theoretically, additional power transfer will be available between the positive and negative pole. However, due to the asymmetric powers, a DC current will flow through the transformer windings and lead to the cold saturation of the transformer. This could result in malfunction of the whole system. So here, the solution is to replace the original transformer to a center-tap transformer, so that the DC current of each pole can flow into the transformer windings in the opposite direction, and induced flux of the DC component can cancel out with each other, so that the cold saturation is avoided. So to what extent can this method work? Let's take a look at its equivalent circuit. The equivalent circuit of the MMC can be seen as the combination of the AC and DC equivalent circuit. From the DC equivalent circuit, it can be seen that DC current flowing through the positive and negative poles are different when transferring asymmetric powers. However, the DC current flowing through the transformer windings are identical, but with opposite direction, and the sum flow together to the ground conductor. This implies that despite the existence of DC component in the transformer windings, Their excited magnetomotive forces can cancel out with each other without causing transformer co-saturation. And from the AC equivalent circuit, it can be seen that the AC arm current consists of a common mode component and the differential mode component. An equivalent circuit can be further simplified to the one that resembles a triple active bridge, except that the equivalent inductance are vertical symmetric. This features a much simpler power characteristics compared to the real triple active bridge, which will be explained in the next slide. As seen from the equivalent circuit, the common mode AC current is able to transfer energy between the two poles, while the differential mode AC current transfers the energy between the primary and the secondary side. The power characteristics under this bipolar operation scheme can be derived by the piecewise calculation. From the analysis, it can be seen that the total power delivered from the primary side to the secondary side is determined by the common phase shift angle, which is the phase shift angle between the equivalent AC voltage of the primary and secondary sides. As seen in the figure, they almost have a linear relationship. The same conclusion can be drawn to the power transfer between the positive and negative pole, which is determined by the differential phase shift angle, which is the phase shift angle of the AC voltage of the upper and lower arms. As for the DC power, it can be simply calculated with the multiplication of the DC voltage and current. On steady-state operation, the DC and AC power should be equal. Through the power analysis, it can be concluded that it is possible to regulate the power of each pole independently, which is essential for the bipolar operation. Another thing of concern is that whether its bipolar operation scheme results in a penalty of increased arms current stress on the power semiconductor devices and transformer. As shown in the first equation, the arm currents of the MMC on the primary side includes both AC and DC components. From the previous analysis of the DC power, the DC component of each arm current is proportional to the power of the corresponding pole. And from the analysis of the AC current, the AC components of two arm currents are also proportional to the power of the corresponding pole. This equally means that the current stress of the semiconductor devices in each arm is approximately proportional to the delivered power in the corresponding pole. Therefore, by manipulating the DC and AC components of the arm current, the positive and negative poles can realize fully independent operation. And moreover, no additional current stress imposed on the semiconductor devices as long as the maximum transfer power is the same with the monopole operation. And as for the transformer current, it can be derived that the maximum value of the transformer current occurs in balanced situation, and therefore no extra current rating is required for the bipolar operation. Next, the proposed bipolar operation scheme is verified by a downscale prototype, and two typical operation scenarios are tested. The first one is the independent power regulation of two poles, which includes the normal operation and the single pole operation. And the second scenario is the voltage balancing capability when the asymmetric power consumptions take place. Firstly, the performance on the normal operation is tested. The positive pole power reference is at 1 per unit, while the negative pole power reference runs from 1 per unit to 0 per unit. It can be seen that the positive and negative pole DC link currents are controlled independently and the powers of the two poles track the reference with good performance. The peak of the upper arm current remains almost unchanged, since the power of the positive pole is constant, while the peak of the lower arm current decreased to almost zero as the power reference of the negative pole runs down to zero. Therefore, it can be verified that independent power regulation of two poles can be realized, and the arm currents are approximately proportional to the powers of the corresponding poles. Also, the transformer current is approximately proportional to the total power transfer between the primary and the secondary side. Hence, the bipolar operation does not result in extra stress on the power semiconductor devices or the transformer. The dynamic performance is also tested when the negative pole of the MMDC-based DC-DC SST should be isolated from the main circuit for maintenance. At first, initial powers of the two poles are both 0.5 per unit. When the monopole operation is initiated, the negative pole power reference ramps down to 0 per unit, and the positive pole power reference ramps up to 1 per unit to maintain the total power transfer. When the negative pole power reaches 0, the submodules of the negative pole are blocked, and the negative pole can be isolated from the main circuit by opening the pre-installed mechanical disconnector. At the same time, the positive pole can continuously deliver power to the secondary side, and the transformer current remains almost unchanged. This verifies the capability of the single pole operation in the proposed operation scheme. And for the second operation scenario, the balancing control to maintain symmetric pole voltages is tested. When asymmetric loads and sources connected to the two DC poles, the disturbance takes place. However, two pole voltages are maintained identical in the meantime. The SST transfer constant power from the primary to the secondary sides, and consequently, the envelope of the transformer current waveforms remains almost constant. This further verifies the effectiveness of the proposed operation scheme. And to summarize today's presentation, a bipolar operation scheme is proposed for the MMC-based DC-DC SST for the interconnection between the bipolar MVDC grid and an LVDC grid. The bipolar operation capability can be enabled by the center-tap transformer, which relies MMF cancellation to prevent from the transformer core saturation under asymmetric operation. The independent power regulation of positive and negative poles, as well as the monopole operation, can be realized, and no extra stress on the components is added. Since no additional power converters and components are required, this method assures higher efficiency compared to the voltage balancer counterpart. So that's all for today's presentation. Thank you all for your time and participation. And you can reach me at my SNU email address for any further questions. Thank you once again, and have a great day.